had a chance to look at the definition of a mapping class group. So today we'll be dealing with what is called a hyperbolic structure on a surface, which was previously defined by Krishnenduda, but I'll go over that again. So while dealing with mapping class group, we were not dealing with any kind of structure on our surface, right? It was basically topology. So topology was sufficient to define and whatever we did last time. But now we are equipping our surface with a structure which is called hyperbolic structure, right? So how do we define a hyperbolic structure on a topological surface S? It's basically an open cover, okay? So you have some open subsets of your surface which cover your surface. So the union of all these U alpha, say, is equal to your surface S. And also you have a collection of maps, continuous maps. So phi alpha, let's call. So phi alpha is from some U alpha into the hyperbolic plane H2. Okay. And they have some properties. So first of all, the phi alpha, for each alpha, the phi alpha from U alpha to the image of U alpha, which is a subset of H2, is a homeomorphism. Okay. And suppose you have two elements, U alpha and U beta, okay, two elements from your open cover. Suppose they intersect, okay. So their intersection is non-trivial, so it's non-empty. So then what you do, you consider the composition of phi alpha with phi beta inverse, okay, which is defined from phi beta of U alpha intersection U beta to phi alpha of U alpha intersection U beta. Okay, these maps, all these, you vary this alpha and beta, or whenever U alpha intersection U beta is non-empty, all these maps you have, these are basically restriction of isometry of some isometry of H2. Okay, so as you can see, both these domain and codomain are subsets of H2, right? The hyperbolic plane. So you can talk about restriction of an isometry, namely the Mobius transformations. Okay, so these two, if these two conditions are satisfied, such a collection of open sets in your surface S with these maps phi alpha, we are calling it as a hyperbolic structure on our surface S. Okay. So any doubt, any questions regarding the definition of hyperbolic structure?
Are you only saying isomorphism? That's all, means continuous 1 and inverse continuous. That's all, right?
You mean the phi alpha? Yeah, these are homeomorphisms.
Homeomorphisms, yeah. But I mean, so is there more structure, like in real manifolds? You have this analytic structure, right? So is there some such thing here?
I don't think we are assuming any such thing.
Okay. Thank you.
Yeah. Okay.
So
yeah.
Neeraj, sorry. So you have a condition on the S. This is only possible when S is hyperbolic. So if this is not always possible, that a phi alpha composition phi beta inverse for all alpha beta will be isometry of H.
No, we are defining what is called a hyperbolic structure on a topological surface, right?
And it may or may not exist.
Oh, it may or may not exist. So it may not exist for every surface. Okay.
Yeah.
Okay.
We are defining if these two conditions are satisfied for some
of course,
alpha.
Yeah. No, of
That's
course there
the,
are surfaces. Hyperbolic structure does not exist.
yes, yes,
It
yes.
is
That's an
sphere.
point. Like,
On
yeah,
sphere there is no hyperbolic.
yeah. That was my doubt. Yeah. Okay. Okay. Yeah.
Right.
Yeah. Sorry for. Yeah.
Yeah. So for that, since you mentioned this, I think the condition on the surface is Euler characteristic should be negative, or at least Krishnanuda, what is the condition? I think that is the condition, right? So if the Euler characteristic of the surface is negative, then we can have such hyperbolic structure, I think.
Yes.
So in particular, if you
Yes,
have
yes.
a genus, if you have a genus G surface where G is at least 2, okay, greater than equal to 2, then this condition is satisfied, and uh, you can give a hyperbolic structure. But I think that construction is involved. Let's not go into this, okay? So we have seen what is called a hyperbolic structure on a surface. Now, can we have some examples? Okay, by example I mean, how can we have some simple uh, hyperbolic structure given on a given topological surface? Okay, so for that, what we will do is, uh, there is a theorem which says that given three positive real numbers a, b, c, okay, you can have a right angled hexagon. What is the meaning of that? So my drawing will not be perfect. Okay, so this is a hexagon in H2, and by right angled hexagon means these angles are pi by 2. Okay, so what is the statement we are talking about? Suppose you have three positive real numbers a, b, c. You can always find a right angled hexagon in your hyperbolic plane such that the alternate sides, say this, this, and this, their lengths are these three positive real numbers. Okay, so suppose such a triple is given to you, a, b, c, and assuming that this is true, what you can do is you can take two copies of this hexagon and glue along the other alternate sides. Okay, so what exactly will happen? So suppose you have another such exactly same isometric copy of the same hexagon, and you have these C, B, and A. What we are doing is, you consider this side as red, okay? Let's color the other side as green, okay? And say the other side is violet. Now what we are doing is, we are gluing this red side to the red side as an isometry, okay, using an isometry, and green side to green side, and purple or violet side with the purple side, okay. So after we glue this, what will happen? What we will get? Can somebody Guess. We'll get some surface, right? What will be the surface? Someone?
Sphere with 3 holes.
So sphere with 3 holes. Exactly. Exactly. Let me draw it. So suppose you glue these two. You will get something like this with some property, right? What is the property? Namely, these length of these boundary components will know, right? So the lengths will be 2a, 2b, and 2c, right? If it's not clear to you, let in this A side and C side, namely this arc will be red, okay? Between A and B, we have green, something like this. And between B and C, we have purple. Okay. So we have managed to get we're calling it as a pair of pants. Okay. So it's called a pair of pants. So we have managed to get a pair of pants which is constructed using two polygons from the hyperbolic plane. So this has a hyperbolic structure, right? It is a hyperbolic pair of pants. Okay, and we know the lengths of the three boundary components, namely 2a, 2b, and 2c. And mind it that this ABC are in our hands. We can choose any ABC. It's up to us. Given any ABC, we can construct a hyperbolic pair of pant where the boundary components have these lengths 2a, 2b, and 2c. Okay. Now there is something called a pair of pant decomposition. Given any surface, okay. Let me show it.
Soumya, can you also comment on why this actually orthogonal sides are needed?
Right.
Yeah.
So you see, because these angles are 90-degree, so after gluing, okay, after gluing, this total angle is actually 180-degree. So say suppose this angle will be 180-degree. All these angles are 180 degrees. So this will that these geodesics. Okay. So yeah. So now there is something called pair of pant decomposition of a surface. What is that? Let me tell it for genus G surface. Say for simple surface like genus 2, okay. Given any such surface, you can always find a collection of finitely many simple closed curves on your surface. For example, you can choose this curve, maybe this curve, and this curve, such that if you cut along these closed loops or closed curves, what you will get is a finitely many copies of pair of pants, right? I hope you can see. So if you cut along these three red curves, you will get two pair of pants, right? There is no geometry here. It's a topological construction. Okay. So now you see, suppose you want to, so out of these pair of pants, you want to come up with a hyperbolic surface. What you will do, right? So you want to go backwards. So here we had started with a surface, a topological surface, and then we considered a pair of pan decomposition and cut along these pair of pan curves, right? These red curves. What you will get is a set of topological pair of pans. Now, using this construction, okay, suitably choosing these lengths, what you can do is, so let me draw here. So suppose you have, from here you have achieved two pair of pants, right? After cutting. These are topological. There is no hyperbolic structure yet. We're going to give some structure, okay? Right? Now, what exactly we want? We want to give a hyperbolic structure to this surface, right? So to glue everything back to our surface, we need the length of these two sides to be equal, right? As this will be glued. Same for these two sides. These two lengths should be equal, and these two lengths should be equal. And these can be anything, right? Given any length, say we choose some A here, okay? Some, or let's not use the same notation, something else. Say some length P, Q, and R, whatever we want. You can consider these construction and give a hyperbolic structure on each of these pair of pans such that the length of these two are R, this is Q, and this is P, and this is P. And when you glue back, what you get is a hyperbolic structure on your initial topological surface, right? And we know that after gluing also, these lengths are fixed, like whatever we have assumed, right? This is Q and this is R, right? So we have given a hyperbolic structure on this topological surface that we started with. Is it clear? If not, I can repeat. So we are starting with a topological surface. We are considering a pair of pan decomposition. So basically we are choosing these red curves on our surface. We are cutting them, and then we are fixing the lengths so that these pairwise lengths are matching, and using these construction from right-angled hexagons in from H2 and choosing these lengths ABC as our whatever we have chosen PQR or maybe P by 2, Q by 2 and R by 2, right? We'll get a hyperbolic structure on each of these pair of bands and then again glue back to create a hyperbolic surface. Okay. Now let me define. It was already defined by Krishnendu. So what is called a type-molar space of given any surface? So for simplicity, we'll be using this SG surface. So basically closed oriented connected surface of genus G, where G is greater or equal to 2. Okay. Now what is the type-molar space? We're calling it as tau S. Okay. So tau S is basically, you consider all pairs X comma F, where X is a hyperbolic structure on the topological surface S, okay? And this F is a homeomorphism from this topological surface S to the hyperbolic surface X, okay? And we call this F a marking, okay? So these are marked hyperbolic structures, okay? But there is a equivalent condition here. So we are considering the equivalence class, okay, equivalence relation we have. What is that? So whenever you have a isometry alpha from X to Y such that alpha composed F is homotopic to G, then we say that X comma F and Y comma G, these two elements from your set, this set, they are equivalent. Okay. Let me again repeat the definition. So suppose we start with SG. SG is the, sorry, it's a closed oriented connected surface of genus G. Okay, and we are taking G greater than or equal to 2. Now, what is this type-molar space? We will consider all pairs X comma F, where X is a hyperbolic surface on which is homeomorphic to S. Okay, so basically a hyperbolic structure on our topological surface S, and F is a homeomorphism from S to X. Here S is our topological surface, X is the hyperbolic structure or hyperbolic surface, and we are calling such a homeomorphism a marking. Okay, but again we have a equivalence relation between all these pairs. What is that? We say that X comma F is equivalent to the pair Y comma G, okay, if there exists an isometry alpha from X to Y, right? All these X and Y are hyperbolic surfaces, so we can talk about isometry, okay? There is a metric such that alpha composed F is homotopic to G. Yeah, Krishnendu.
No, nothing. Go ahead.
Okay. So, is it okay, the definition?
Do you want homotopic or that isotopic? Iso, the in-between maps being isometry, something you were saying, no?
Isotopic.
Isotopic.
I think standard definition is homotopic, but
I don't know, I'm just asking you.
Right. Yeah. Maybe.
Isotopy will also work.
Because in case of surfaces, I think isotopies and homotopy are giving us same class, right? Something, yeah. There is a theorem like that, I think. Yeah. Okay. So this is the definition of diagonal space. Now, what is so we talked about this action of the mapping class group on the diagonal space. What is this action? You start with some mapping class psi from mod S, and some element from your diagonal space, say x comma f, this pair. You define psi acting on this pair, this class of x comma f, as the class of x comma f composed G inverse.
Hello, Soumya.
Yeah.
Yeah. So, how you give different hyperbolic structure on the same surface? I mean, how it parameterize actually? Because at least can you give two hyperbolic structure on same surface, maybe on torus or Hyergenus?
Yeah.
Two torus.
On torus, there is no hyperbolic
Yeah.
structure.
Okay. Yeah.
So
Maybe.
for example, here in this example,
Yeah.
this lengths P, Q, and R,
Yeah.
as I said, these are in our hands, right?
Mm-hmm.
So if you choose some different positive real numbers, okay, and you do this previous construction, instead of A, B, C, say 2, 3, 4, you choose 4, 5, 6,
Yeah.
and you do the same construction, you will get two different non-isometric hyperbolic structure, because the lengths of these curves will be different.
Yeah.
So in fact, this is giving us an uncountable family of hyperbolic structures on our surface.
Yeah. Yeah. Okay.
So maybe I can also talk about the Fenchel-Nielsen coordinates. Maybe that's what you were referring to.
Yeah.
So yeah. So let me first define the action. So again, so you have one element from your mapping class group, say psi, and one element from your diagonal space, say the class of x comma f. You just define psi acting on this class xf to be the class of x comma f composed G inverse. Okay, this is the action where this G is any representative from your psi. So this means even if you choose some other representative, these two will give you same class. Okay, this needs to be checked. Okay, so yeah. So before going into the theorem that maybe I aim to talk, I mean give a sketch of proof of that. But let me talk about this Fenchel-Nielsen coordinate before this. So I'll start from here. Okay, so here. So I'll briefly talk about it. So so here what we are seeing is you start with any surface S, and suppose you have a pair of band decomposition of that. It can be checked that always the number of pair of band decomposition, I mean the number of band curves for a genus G surface is 3G minus 3. Okay, so in case you have a genus G surface, okay, it's a genus G surface SG, you can consider these curves. So this okay. Similarly, here you have
Is the hyperbolic structure defined only on hyperbolic manifolds?
no. We are starting with a topological surface, right? There is no hyperbolic structure initially. We started with a topological surface, okay? And suppose we have a band decomposition of the surface. Then from pair of bands, you go to hexagons. And on hexagon, you have the choice of these three length parameters, the length of the alternate sides, right? And once you choose them, then that gives you a hyperbolic hexagon. From there, you go to hyperbolic pair of bands. And then suppose you have these matching criteria, the length of two boundary components which are being glued the length should be equal. Suppose you have that, then you go to a hyperbolic surface. Okay. Right. So suppose you have such a surface SG, topological surface. There is no hyperbolic structure yet. And suppose so you can check that the curves that I have drawn here will give you, in fact, a pair of band decomposition. Okay. This is not unique. Okay. There can be other set of curves which will give you another pair of band decomposition. But the number of pair of this red curves given SG, given this genus G, okay, for SG, you have exactly 3G minus 3 band curves always. This can be checked. Okay. Yeah. And then what you do, so for each of these red curves, as we have just seen, these lengths are up to our choice, right? We can choose these lengths. So for any element from the, so you consider positive reals, right? Let us denote that as R plus. And you have how many curves? 3G minus 3 curves, right? So you have a 3G minus 3 copies of this R plus, right? That many choices you have for these. So you consider R plus to the 3G minus 3. Okay. So for each of the point of this set R plus to the 3G minus 3, you get a hyperbolic structure here. But then there is another set of choices involved here. Okay. What is that? You see, while gluing back at the last step, when you have already given hyperbolic structure on these set of pair of bands, okay, suppose you have already given the hyperbolic structure on these, and you only know that the length of these two, say these two lengths are matching, these two lengths are matching, and these two lengths are matching. That much suppose you know. Okay. Still, while gluing, what you can do is, instead of gluing them as it is, okay, you can rotate one of them by an angle theta and then glue, right? So suppose these two are your this is one boundary component and this is your another boundary component. Let me draw these here. Suppose this is one boundary component, this is another one, right? and you have like this, right? So we want to glue them isometrically, right? We already have length. We know the structure on these two hyperbolic pair of bands. So while gluing, we have a choice, right? How many choice? So for each real number, you can rotate. So for each theta belonging to R, you can rotate the right hand side boundary by an angle theta and then glue. Okay. So for each of these red curves here, namely 3g minus 3, you have R many choices. And these are called twist parameters. Okay. This theta is a twist parameter. Okay. And the previous one, these lengths, the lengths of all these curves, P, Q, R, these are called length parameters. So this is basically giving us length parameters. And you have another set of choices, R to the 3g minus 3. This is coming from the twist parameters. Okay. And now it's a involved theorem that this, okay, you see it has already a topology. It is not just a set. R has a topology, so R plus has a topology. So R plus to the 3g minus 3 has a topology, R to the 3g minus 3 has a topology, and you have a cross product or product topology. So the whole thing, okay, this side is a topological space. And for each of these choices of length parameters and twist parameters, suppose such a 6g minus 6 tuple is given to you, okay, 3g minus 3 plus 3g minus 3 is 6g minus 6. So suppose such a tuple, 6g minus 6 tuple is given to you. This will give you an element of your Teichmuller space, right? This will give you a hyperbolic structure. This will fix a hyperbolic structure. So there is a map. And in fact, it can be shown that they're bijective and it's a homeomorphism. Okay. And as a whole, these two set of parameters are called Fenchel-Nielsen coordinates. Yeah, Neeraj.
Yeah, sorry, I think I missed something. So when you are saying this is a homeomorphism from R to R to the power 6g minus 6 to tau s, which is a Teichler space, what exactly topology you are assuming on tau s? Or you are pull backing the topology of the R to the power 6g minus 6?
That can be done, but by when you are saying two topological spaces are homeomorphism, both should be topological spaces, right?
Yes.
So this has already been discussed in the talk of Krishnan Duda.
Okay.
So
Yeah, maybe I missed that. Sorry.
Yeah, he gave another definition of the Teichmuller space in terms of representations from pi 1s to PSL to R, right? Namely discrete faithful.
Yes.
And from there he said that this is sitting inside like as a quotient of PSL to R to the 2g. So from there it's coming, the topology.
Okay. Yeah, thanks.
So all right, any other questions? Yeah, okay. So let us go to the last part of our discussion. Can you repeat what is R plus? Okay. Yeah. So namely these length parameters, right? So uh, so what we want? We want to parameterize the set of all hyperbolic structures on our topological surface. So what do I mean by parameterizing? I mean we want to number them. Somehow we want to give a bijection. Okay. To each of them, we are associating a tuple. Okay. Uh, so tuple means it has 6G minus 6 components. Okay. The first 3G minus 3, the first half of this tuple is coming from these length parameters, and the next set of next half 3G minus 3 components of the tuple are coming from the twist parameters. Now what is these length parameters that we have discussed here? What we discussed, you start with any topological surface as here, right? And you choose any set of pair of Pant curves, like these red curves I've chosen, right? And the point that I tried to make by these construction, from starting from hexagon and this is saying that these red curves, the lengths of these red curves are in our hand. Whatever length we choose, okay, whatever length, suppose you give me 3 positive real numbers, I can construct by these constructions, these steps that I've mentioned, I can construct a hyperbolic structure on these genus 2 surface, topological surface, right? Such that the lengths of these red curves will be exactly the same lengths that you mentioned, those 3 real numbers, positive real numbers. Okay. So as these are positive real numbers, this is coming from R plus. Okay. So in case of genus 2, how many are there? 3, right? So you put this 3 times 3G minus 3 will be 3 times 2 minus 3, that is 3. In case of, say, genus 3 surface, it will be 3 times 3, that is 9 minus 3, it's 6. Okay. So 6 lengths will be there. Lengths means positive reals. So from there it's coming. Is it fine? And similarly, the twist parameters that I have mentioned. So those are coming from reals, right? There is it need not be positive angle. It can be negative angle as well. So we are taking R, the whole R. Yeah.
Yeah. So how can you assure that two different lengths give two different hyperbolic structures? For example, if you take R1, R2.
Yeah, that I think is a part of this theorem that I did not prove.
Yeah.
So
Okay.
this will give a bijection, right?
Yeah.
So
Yeah.
it will be a 1 1 and on 2 function. So, yeah.
Okay. Yeah.
Okay.
So actually, the length corresponds to the trace of the uh, hyperbolic elements that represent the fundamental group. Okay.
Right.
And you know that the trace is a conjugation invariant. So that's why different length will give you different representation of this fundamental group of pair of pans. All right. So that will corresponds to different hyperbolic structures.
Okay.
Okay.
So
Sir,
yeah.
Yeah.
Sorry, sir.
So Neeraj, you were saying
Can
something.
we use it just? Yeah. So sorry, I was just disturbing. So I'm saying, can we just use the pan decomposition again? So if you have a two different curves, which you have a curve which have a different length, you decompose in the pan decomposition, then you get a pant which is have a different length, and two different pants cannot be isomorphic, which I think the first lemma Samudra was saying in the starting, that using the hexagon.
That's okay. So that's what I'm saying. That is also maybe that in that direction also one can give another interpretation.
Okay,
Okay.
okay.
But
Yeah.
I mean, what are these lengths that 2A, 2B, 2C? They corresponds to the trace of the uh, element that represents the fundamental group. Okay, so there
Okay,
is a,
okay, okay.
I mean, you take any, when if you lift that, then that will correspond to the axis of a loxodromic element, right? So that you can relate to the trace
So
of the element. Okay,
so looking at the
so
Mobius transformations. Yeah.
yeah, looking the lift to SL2R of
Yeah.
the representation.
P
Yes.
PSL2. Ah, okay, SL2. Yeah. Okay. 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 Thanks.
Yeah. Any other questions? Okay. So we have already defined what is the action of the mapping class group on the Teichmuller space. Now it's a theorem, in fact, an involved theorem, which says that this action is properly discontinuous. So if you remember, it was defined by Krishnendu in the last lecture, his last lecture, I think. So what is a properly discontinuous action? So suppose you have some space, okay, X, on which some group G is acting, okay. You say this action is properly discontinuous if whenever you have some compact set, say K, okay, and you consider all the orbits of this K. By orbit, I mean G, so some small G you take from G, okay, and you consider G of K, okay, G times K, G acting on K. So it may be somewhere here, or it may intersect this K, right? For some G1, it may intersect, right? So you consider all the orbit elements of K which intersect this K. That number of such orbit points should be finite, okay, and this should be true for all compact sets K. For every K, you consider all G such that K intersection GK is non-empty. That set should be finite. Okay, this was the definition of a properly discontinuous function. All right. Now, in this case, we are acting this mod S, namely the mapping class group of S, on the Teichmuller space, right? And we want to prove that this is properly discontinuous. I'll not give a full proof, but the main idea of the proof is as follows. We go by the method of contradiction. So suppose not. Suppose this action is not properly discontinuous. So what you get? This will imply that there exists a compact set K in your tau S, right? And there will be some sequence psi n in mod S, okay, of distinct elements, right? Such that what will happen? Psi n of K intersection with K will be non-empty for every n. So for every psi n, this will happen, right? For some k, this should happen. Now, what will this imply? So you have a sequence of distinct elements, psi n, and you apply on this k, and the intersection is non-empty for every such psi n. This will say that there exists a sequence xn in K where this xn is a hyperbolic structure, right? It is an element of diagonal space such that psi n of xn will belong to K for every n, right? So you have a sequence in your K, the compact set K, such that the image of these phi n of xn, this belongs to K for every n. Okay, this much is okay, I think, for everyone. Now we will need one definition. Okay, it is called a length function of a curve. Okay, so given any gamma, which is a simple closed curve on your surface, what you can do, you can define a function, okay, L of gamma from the Teichmuller space to R plus. Sorry, initially the previous one I put the plus in the bottom, so I'll do this. So what is this function? So L gamma of some element, say xf, okay, some class of xf, this will give you the length of f gamma in X. And what is the meaning of this length of f gamma? We'll again use another theorem which says that see, gamma is a curve, right? So f of gamma will be another curve in, so let me draw it. You have S here, okay, this is our S, this is our F, and this is our hyperbolic surface, right? This is the marking F. Now you started with some gamma, say this one, this is our gamma. Okay, where will be this f of gamma? It will be somewhere here, right? This is our f of gamma. Okay, now what this notation is telling us, in the isotopic class of this f gamma, there is a geodesic, in fact a unique geodesic. Okay, this is a theorem that this will exist. Okay, so you consider that unique geodesic representative from the isotopic class of your f gamma, and it has a length, right? It is basically the shortest curve in that isotopic class. You say that the image of your xf is that length. Okay, let me repeat. You start with some gamma, which is a simple closed curve on your topological surface S. Okay, so associated to that gamma, that curve gamma, we want to define a function from Teichmuller space to the set of all positive real numbers. What you are doing, you start with some you start with some marked hyperbolic structure, namely the element, some element from your Teichmuller space. So you have x comma f, and you consider the image of gamma via the marking. So now f of gamma sits inside the hyperbolic surface. Okay, you can talk about lengths here, right? So you have a curve in your hyperbolic surface x. Now this theorem says that there is a unique geodesic representative. Okay, there is a geodesic which is homotopic or isotopic to this curve f gamma, right? And that should be unique. There is no other geodesic in that class. So you consider the length of that particular geodesic and you say that L gamma of xf is that length. Okay, right. So this is the definition of a length function, and it's a fact, it's a theorem that for every gamma, okay, for any simple closed curve gamma, the length function is continuous. Okay, so L gamma is continuous. So we'll be using this fact here now in the proof. So let me go to the last part of the proof where we left.
Shall I make one comment? Just correct me.
Yeah.
You told that you have some unique geodesy representative. There is the where you first time using that you want a surface to be closed surface without puncture. You can do everything for a surface with puncture also, right? Your whole theory.
In our case, we are dealing with closed surfaces. But if you have a puncture,
That unique geodesy representative there, if it has puncture, there is some catch that I know.
okay. Yeah, but for closed surface, there is no catch, right?
Yeah.
Okay.
But maybe Krishnan sir, will this same definition works in case of surface with puncture, hyperbolic surface? Yeah, okay,
Yeah.
I can ask at the end.
Yeah, maybe we can discuss at the end. So the proof goes like this. You have a sequence xn in K such that psi n of xn is in your K, right? And you know that K is compact. So now you have you consider any two curves alpha and beta that fill the surface S. So what is the meaning of a filling? We will not be using this in the last part because I'm not going to tell you the entire proof. So let me tell you what is the meaning of a filling. This means that if you remove these alpha and beta from your surface, okay, what you will get is a disjoint union of disks. Okay, so you have such a pair of curves, alpha and beta. Now you see, corresponding to alpha and beta, you have the length functions, right? You can talk about L of alpha and L of beta, and these are continuous, right? But now, as this K is compact and this L alpha and L beta are continuous, what you can see is there is a bound on each of these, in fact. So L alpha of x and L beta of x. As x, this x is coming from our K, okay? So there is a universal bound R such that L alpha of x plus L beta of x is less equal to R for every x in our K. Okay? Now, this part I'll not be proving. So you can it's a claim that you can show if you consider this L of psi n inverse alpha, this is a curve, right? And of xn, this diverges. Okay, and if you see that this is basically equal to L alpha of psi n of xn, and this psi n of xn is coming from your K, right? So this is basically contradicting these two facts. So this and this are contradictory. So there is a contradiction. Okay, so I'll not be proving this claim, but this is the idea, the main idea of the proof. Okay, yeah, maybe I'll stop here.
So thank you, Soumya, for your nice talk. So any comment or question?
Hello.
Yeah, Christian.
Ah,
Yeah.
yeah. So I think that question, that why the if you determine those lengths of the boundary curves or the boundary geodesics of a pair of bands determine its hyperbolic structure. Okay, it also follows from the picture that some wrote about hexagons. Okay, so you are
Which one?
essentially getting a pair of bands, hexagon. So you are getting a pair of pan by gluing two hexagons, right?
Yes.
Right. And these three lengths determine a hexagon up to isometry. Yes. So this ABC, I mean, given ABC, there is a unique hexagon up to isometry, right?
Yes.
Yeah.
You know this as well, no? I think, yeah. Yeah, so you are getting pair of pans just by gluing such hexagons, right? So that gives that as soon as you fix this boundary lengths, up to isometry, there is a unique pair of bands. So there is a unique hyperbolic structure. So when you change the length, your underlying hexagon changes, and hence the hyperbolic structure also changes. So probably this is what Neeraj was trying to say.
Yeah. Thank you, sir. Thank you for the information.
So where you find this proof of this argument that um, up to isometry you get unique hexagon for given length ABC?
Oh, so there are. I mean, this is I think a standard result in hyperbolic geometry. Okay, so you can, for example, look at this book by Fencher called Hyperbolic Geometry, or there is a book by Peter Busser. And for all these, I think the best book would be the one which I mentioned yesterday, that Martelly's book. Okay, that's a nice book. Yeah. Also, there is a book by John Hubbard on Teichmuller theory, but that's much more extensive. I mean, they have there you can get different approaches to the Teichmuller space.
Okay. So any other comment or any query questions?
Yeah,
I have
Praveen
a
was.
question.
Okay.
Sorry.
Yeah,
Later.
ma'am. Yeah. No, please go ahead, ma'am.
No, I saw something about Fuchsian surface here, and Krishnendu talked about Fuchsian groups, no? So they are just discrete subgroups of PSL2R, but why are they called Fuchsian? Is it something to do with the name? I mean, name of the person?
I think there are the mathematician, right? Fuchs, who sort of
Fuchs.
initiated. Yeah. So I think because from there it called Fuchsian.
So same thing about surfaces, is it? I saw something about.
Surfaces, because I think because the Fuchsian groups grip these surfaces.
Okay.
So that's what. I mean, surfaces are the H2 mod a Fuchsian. I mean, you take the orbit space of a Fuchsian group action on a hyperbolic space, right? So that's why it's called Fuchsian.
Okay.
Yeah, Praveen was asking something. Praveen, can you repeat once?
So in your definition is makes sense even if you started with the surface with punctures, right? You assume that your surface are closed surface.
Yeah. So whether that in every isotopic class there is a unique geodesic, that part you were mentioning, right?
Yeah. Can you go to the definition of Teichmuller space?
Yeah. So before I think before Somu answer or Praveen asked the question, I just want to comment here that the original way Fuchsian groups were appeared in the literature was not in connection with hyperbolic geometry. but in connection with monodromy of differential equation. And the work of Fuchs was related to differential equation.
I see.
Right?
So there is some connection there also.
Yeah. So
Okay.
Yeah, Praveen.
Yeah. So here this definition makes sense if you start with even a orientable surface with punctures.
Yeah, I think this definition has no problem. Yeah,
Then
right.
the first place where you are using is that to have that action is properly discontinuous, you need it to be closed surface.
Right. Yeah, I think so. Yeah. Mhm. But I need to check whether for such a punctured surface that theorem is true or not. Whether given any
So this.
any isotopic class, whether there is a unique geodesic or not. Yeah.
Also, are these surfaces hyperbolic surface with puncture? One puncture, can you get them to be hyperbolic?
Yeah, as long as I think the Euler characteristic is negative, there is a hyperbolic structure, and you
Also
can talk
torus
about.
minus a point.
And unique geodesics may be a problem, right? Because if one point is missing, at least geometrically, it seems like that.
Yeah, that I need to check. Yeah.
So how will you define like
If you
straight line?
what is the question?
In case of punctured surfaces, whether this is true that given any isotopic class of simple closed curve, you have a unique geodesic.
Okay. I think it will be true, no, Somo?
I'm not very sure. I can check.
So one day me, George was discussing this one. So we saw that
Yes.
if it is homotopic to a puncture, if our the curves we started with is homotopic to a puncture, in
Right.
that case, that class may not have.
Yes. Other than puncture, it may have.
Yeah.
That's what we discussed, no?
Mm-hmm. We start with a simple closure which is not homotopic to a puncture, then
Then
its class has a
same
unique
thing.
geodesic.
Yes. I think we discussed it, no? One day. Yeah, you were right. With George, we were discussing, right?
Yes,
Yeah. Right. Then did you finish those exercises that you were asking me, including this one?
Oh, we still have some hole. After that, we didn't find
Oh.
common time.
I see. Okay. So these days, what are you up to? Bread groups?
Yes, sir.
Okay, I think there is no more question.
Yeah, okay. So there is no more questions. So let us thank Soumya. And yeah, we'll see again you tomorrow at 3
Yeah.
p.m.
Okay.
Yeah.
So is it at 3 tomorrow?
Yeah, tomorrow 3. You know, every day, daily it's 3.
Okay, so only yesterday was 5, right? Yesterday I logged in at 3 and wondering what was going wrong. Then I
Yeah. So
checked.
have you seen this video recorded lecture?
Well, I thought you sent me a link, sent
Yeah.
me slides. Where is the video recorded lecture?
Okay. So maybe I'll send you the link also. There is actually all the video lectures are there.
Huh.
Yeah,
So
I
I
will,
didn't get that. I only got Krishnendu's lecture slide I got, but not video record.
okay, okay. I will send you. Maybe yeah, Randeep will send you. Yeah, Randeep,
Oh,
please send the link of the video to ma'am. Yeah.
thank you.
Okay, okay,
So
okay. So see you, Soumya, tomorrow. Thank you very
Yeah,
much.
yeah.
Yeah, yeah.
Okay,
Okay,
bye.
thank you.
what is the plan from? So can we stop recording, please?
Yeah,
I
Randeep.
yeah, I'm trying, but yesterday I have tried to stop the recording and the video was disconnected. So I don't know what is the problem going on now.
Okay, so
We'll
Just
try
let
once
me.
again. So what is the plan tomorrow for talk like? Soumya?
I'll be talking about the Nielsen-Thurston classification.
Oh, you're talking about Nielsen-Thurston classification of the mapping classes.
Yeah.
Okay.
okay, okay. Thank you. Okay, thank you. Bye.
Thank you.
Yeah. Bye.